Hello everybody and welcome back. We continue with the International Mathematical Olympiad 2019. So in this video I'm going to show you my solution to problem 5, which is, as you know, considered to be of average difficulty. It's a combinatorial problem. So let's look at the problem statement first. So you have a sequence of length n consisting of letters T or H, which is like coins and head or tail. And you perform the following operation. When you have a positive number k of coins showing H, so if it's not 0, then you turn over the kth coin from the left. And otherwise, if k is 0, it means if all coins are T, then you stop. The first part of the exercise is actually to show that you always have to stop after a finite number of operations. So let's see first how it looks like at an example. So they gave here a simple example. We start with a configuration THT. Here k is equal to 1 because you have only one H. So you turn over the first coin from the left, so you obtain HHT. Now k is equal to 2. So you turn over the second coin and you get HTT, and now k is equal to 1 again, so you turn over the first coin, so eventually you get TTT and you're done. You see immediately that we have k equals to 1 and then 2 and then 1 and then 0, so it's not decreasing each time. Otherwise, of course, the exercise would be trivial. But k can go up and up and up, and then again down, and then again up. But eventually, it gets down to 0. So that's what we have to prove. And the second part of the exercise actually requires you to find the average number of steps that it takes to finish for a given configuration. So it means you have to, for all configurations, you have to consider the number of steps needed, and then to find the average of all these numbers across all 2 to the power of n possible initial configurations. But let's start with the first part. So we have to see that we are actually always terminating, that we always arrive at TTT, all T. Usually when I have an exercise like this, then I start experimenting a little bit and I try some simple cases. So the simplest case is, of course, if we have only one H. So let's look at that case. Let's say it's at position M. So for example, here you have at position 4 your only H. So since you have only one, then you first turn over the first coin, but then you have 2. So then you have to turn over the second coin, but then you have 3. And then you turn over the third coin, and then you have 4. But now actually you have to turn over the fourth, but that's already an H. So now it's going down. Now you will have 3, and then you have to turn over the third one, but that's an H, so you get 2. Now you have to turn over the second one, but that's an H, so you get only one H at the first position. So then you're done, because in the next step you will get all T's. And then you see that for this you need 2 times m minus 1 steps, right? So if you start with position with one m at position m, then with one h at position m, then you essentially need 2m minus 1 steps to finish, and it's clear how it's done. So the number of h's goes up, and then it goes down, down, and then you eventually end up with 0. Now, a little bit more complicated would be if we have 2 H's at positions M1 and M2. And here is one example. So M1 is 4 and M2 is 7. So you have 2 H's at positions 4 and 7. Now you see that what happens is very similar to what we observed here, except that you don't start with the first T and turn it to H, you start with the second T and turn it to H. But then the rest looks really the same. So you see, I go from here to here, from here to here, and then I kill actually this fourth position H. So the first initial H is actually killed in this step. And then I go back and I kill this H, and then I go back, I kill this H as well. So I'm left with only one H, and that's this second H in the initial position. So essentially, I need 2m1 minus 3 steps to kill this first H, and then what remains is just the second H. So for the second H, I will need, of course, 2m2 minus 1 steps. That's what I already concluded here. So in total, I would need 2m1 plus m2 minus 4 steps. Now you may say that we finished the case when k is equal to 2, when we have 2 H coins, but actually that's not the case, because what we considered is not the general case, right? Here I show one example. If you have still 2 H coins, but the first one is at the first position and the second one at the 7th position, then this procedure doesn't look the way we described it here, because we said, well, first you kill the first H, and then you kill the second H. Here's actually the other way around. So we actually first kill the second H, and then what remains is the first H. We see that there is a bit more to it. However, in this case as well, we do need the same number, 2m1 plus m2 minus 4 steps. So maybe we are thinking in the right direction. Maybe it's good. However, we have to adjust it a little bit, as you see here. But now we already got our idea actually what happens in general, because in general you have k H's, and you start by changing whatever is at position k, but then this kind of movement, H's, 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 and then T's, T's, T's in the other direction, that will still happen only locally after the position k, right to the next available H. So, for example, if the position k is H, then we kill it immediately. But if it's T, and then again you have T, 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 and then maybe after 3-4 steps you have the first H, then this H is going to be killed first. And actually you see that in general the first H that gets killed is the one at position Mi, such that between K and Mi there are only T's. And for this, you know exactly how many steps you need. You can just count it, and you see that you need exactly 2 times Mi minus K plus 1 steps. So just like before. And now you're basically ready to make the general guess. Why is that? Because you see that for to kill one H, you need 2 Mi minus K plus 1 steps. But after that, you will actually have K minus 1 H's, and then you will have the same formula with a different Mi, of course, but instead of K, you will have K minus 1. So essentially, we claim that in general, if you have k H's and their positions are M1 up to Mk, then this is exactly how many operations you would need. 2 times the sum of these positions minus the sum of the odd numbers, 2k minus 1, 2k minus 3, down to 3 and 1. And then this sum is known to be equal to k squared. So essentially it's 2 times the sum of the positions minus k squared. So that's our conjecture, but actually not only our conjecture. If you followed this reasoning, then you see that we already have more or less a proof for that. And if you really want to prove it, you can do that by induction. But what I suggest is a very simple and neat induction, namely induction on exactly this number, right? So if you do induction on this number, then you can actually do only one step, because usually when people write down the solution, they write they talk about several steps. So they say, well, you first do this and this and this, and then you kill the first h, and then you go you proceed with the second h, and so on. But actually, if you formulate it like this, you can proceed by induction on this number. So it means if this number is 1, for example, then it has to be the case that that you have this kind of configuration. That means h and the rest is t. And then you're done. So you just have to show algebraically that it's impossible for this expression to be equal 1 in any other case. So only if k is 1 and m1 is 1, can you have this expression equals 1. Otherwise, it's more than 1. And then what happens is that you have to show that if you perform only one step, whatever that step is, but it's always, of course, changing the kth position, that by changing the kth position, this expression always goes down by exactly 1. So that's the magic. So whether k goes up or down, in both cases, this expression goes down by exactly 1. And it's trivial to prove because you essentially only have two cases. So case 1 is if the kth coin is h, and case 2 is if the kth coin is t. So in the first case, k drops by 1 because this h will become a t, and in the second case, the k goes plus 1, right? But then you have one more m here, and then you just have to do your computation. So it's interesting, but if you really have this number, then you don't have to do any kind of process like here. You just consider what happens in one single step. So that's like magic. And then actually, of course, not only are we done with the part A, but actually we are basically done with the part B, just because we already know the exact number of steps that we need. It's this. So what remains is just to find the sum of these guys over all possible choices of k and m1, m2 up to mk. And this is again not very difficult, so it has little to do with combinatorics now. It's almost pure algebra. But remember that in this kind of competition, you really need here your answer in a closed form. Because if you just submit this sum as your answer, well, it's true. Well, of course, you have to divide it by 2 to the power of n. But if you submit that, yeah, that would be correct as an answer, but it wouldn't be accepted because you need your answer in closed form. And that's not very difficult. We actually have two parts to sum. So first we sum this m1 plus m2 plus mk, sum over all possible choices. It's 2 to the power of n minus 1 times 1 plus 2 plus till n. Why is it so simple? Well, you just ask yourself the question for these guys, m1 to mk, they come from the set 1, 2 up to n. And then for any of these numbers, say I, you ask yourself, how often will I see in this whole sum this exact number I? Well, since this number I belongs to 2 to the power of n minus 1 different subsets, then you will see it exactly that many times. So each number from 1 to n you will see exactly the same total number of times, namely 2 to the power of n minus 1. And that's how you get immediately your sum. And finally, for the second part, you have to sum up k squared over all possible choices of k and k positions. So that's essentially sum of k squared times n choose k. And now there are many ways you can do this, but the simplest way actually is to Google a little bit. That's what you cannot do if you're really a contestant, but I wasn't. I just did this for fun, and that was the simplest way for me actually. You just go to Wolfram MathWorld, wolfram.com, and then binomial sums. You find exactly this identity. And then if you take 2 times this minus this, then you obtain your answer, and divide by 2 to the power of n, you divide your answer, which is very simple. So you need on average this many steps. So it's quadratically many steps, and that's what you would expect, right? Because you always go to the left, to the right, to the left, to the right, that many times that you need to reach your h's. So essentially, you go all the way through your sequence, and that you have to do for every single h that you have. So for that reason, you would actually immediately maybe suspect that the average number is indeed quadratic. Okay, so that was all about this exercise. I hope you enjoyed it, and I hope you join for the remaining couple of videos in which I will solve the most difficult exercises in this competition, 3 and 6 for you. So in case you don't understand something or you have question, please drop a comment. I will be happy to help you. So thank you for watching, and have a nice day.